So today I will talk to you about a new and simple approach to understanding the space of effective field theories. It's work done in collaboration with a fantastic group of physicists, which I write here below. And sorry, right. So I don't need to introduce effective field theories to this audience. Basically, the thing I have in mind is effective field theory as a tool to describe physics at the boundary between what we know and what we don't know, or what we cannot calculate. So in this sense, effective field theories, as I will talk about, are useful, for instance, to parameterize physics beyond the standard model, quantum gravity, or any theory at strong coupling, below the strong coupling scale. One aspect that we all love about effective field theories is that in some sense they are model independent. But in order for this model independence to be really useful, so this model independence basically means that we're capturing the broadest possible hypothesis in terms of the UV dynamics from which the effective field theory comes from. And in particular, consider the 222 scattering amplitude, which is basically what I'm going to talk about for the whole talk. For a single scalar at 3 level, this is just a polynomial expansion in energy, which for the 222 scattering is just Mandelstam S and T. So in the effective field theory, different energy behaviors are actually consistent. And this is basically captured by the fact that the coefficient of this expansion can take different size relative to each other. So the question that I will address in this talk is which of these patterns that I just show you are compatible with a UV completion, which is both causal and unitary. So I take the occasion to make you focus actually on this expansion and the nomenclature that I gave to the coefficients. In particular, I label the coefficient as CS, T, where S and T, so the two numbers basically capture the powers of S and the powers of T in the expansion. This table will be recurrent during the talk, so keep it in mind. I will start with a short introduction about effective field theories in the infrared, and basically I will mention what kind of patterns of these coefficients are naturally expected within an effective field theory. Then I will introduce a tool to actually relate this infrared effective field theory with a UV quantum field theory, causal and unitary. These, most of you already know about it. These are dispersion relations, which apply to the 222 scattering amplitudes. But I will also introduce two tools that you might not have seen so far. These are arcs, different ways of building these dispersion relations, and then their interpretation in terms of moments of a positive distribution. This is the big novelty of this talk, in some sense. I will then present the bounds that we obtain from this tool on theories at 3 level. And basically, I will show you that of all these coefficients, most of them are actually, in some sense, bound to be always smaller than the most leading ones. This is not a trivial statement, as I will argue in the first point. And finally, in the last part of the talk, I will discuss more in detail loop effects, and basically how the bounds that we naively derive at 3 level are modified when we actually look into the realistic situation in which also some infrared loop effects are taken into account. Okay, good. So in terms of the field content of the effective field theory I will talk about, it's very simple. For most of the talk, it's just going to be a single scalar, pi, or it's not even going to be named. And in terms of symmetries, I'm not going to assume any particular symmetries, apart from sometimes you will see a shift symmetry just to basically motivate certain patterns in the effective coefficient. So very simple theories, just for you to understand as clearly as possible the juice of the physics behind. So let me start with a picture from the infrared, low energy, only within the effective field theory. 2-to-2 scattering, as I said, and we look at the amplitude square as a function of energy. So an effective field theory at the scale m is the cutoff of this effective field theory. If we assume that the UV theory is generic, that it doesn't possess any particular features, then the effective field theory is also generic. And it can be captured by an expansion of this form, which in this case I've singled out the powers of the cutoff explicitly. I will not do this throughout the rest of the talk, but for this part it's going to be clear, as you will now see. So within the effective field theories, the coefficients run. And indeed, as energy changes, the coefficients change their size. I hope you appreciate it. These little bars becoming bigger and smaller. So one question that we might ask is whether these coefficients can actually be hierarchical with one with respect to the other. For instance, is it possible to have the first few coefficients big and then the remaining one smalls in units of the cutoff? Well, you see that running within the effective field theories actually tends to homogenize the coefficients. This is why we think about natural effective field theories as theories for which the coefficients are more or less of the same order. There are, however, different patterns of these coefficients which behave differently. Indeed, a pattern like this one, where only less relevant coefficients are turned on, while the most relevant ones are small, under running doesn't get homogenized. And this is because there are certain approximate symmetries that protect softer patterns. I'm sure you're familiar with this. For instance, the case of a Goldstone boson is accompanied by a shift symmetry, pi goes to pi plus a constant, so that in the Lagrangian, it actually appears always with a derivative. Interactions have one derivative per field, and then the amplitude for 2-to-2 scattering grows at least like energy to the 4. So in that sense, there is no constant coefficient. Galileon's is another example of this type. The shift symmetry is a bit more complex. It has also a piece proportional to x, meaning that a Lagrangian invariant under this shift symmetry, oops, sorry, this is the problem of having these animations that if I, zack, okay. So because of this shift symmetry, the Lagrangian has to have two derivatives per field, and the amplitude goes like energy to the 8. There's in fact a piece also energy to the 6, but it's a bit more complicated to explain, so I left it out. And this can be generalized to what I call super soft, so just a generic shift symmetry for which the amplitude starts at some very high power of the energy. And I reiterate that an amplitude like this is natural from and consistent from the point of view of the effective field theory. So one of the questions that I will address in this talk is whether these super soft theories can actually be UV completed in quantum field theory, where when I refer to quantum field theory, I'm just thinking about causality and unitarity. So the tool to answer this question and actually paint the map of quantum field theory, I'm going to introduce it now, and is this tool of dispersion relations. Many of you might be familiar with this. And to begin with, I will just consider the forward scattering, so at zero impact parameter, where the amplitude is just, the two particles just go on in the same direction. In this sense, the amplitude is just a power of the energy. This is things which are more or less well known from the 60s and the seminal work from 2006 by Adams and Akani Ahmed and et al. So in this situation, the amplitude is just a function of the energy, Mandelstam S, the energy squared. And particularly, I want to translate the physical properties of causality and unitarity into some mathematical properties of the amplitude, of the 2-to-2 forward amplitude. And causality translates into the amplitude being analytic for complex S. So we work in the complex S plane, and it's analytic up to some singularities in the physical region. So for S real and above threshold, above 4m squared, basically there is a branch cut. Because of crossing symmetry, this branch cut also appears in the U channel, which is equivalent to negative S in this setup. And in addition, there are poles at the origin just because the object that I'm actually looking at is the amplitude divided by certain powers of S. Now, in the complex S plane, basically, it is divided in two parts. One region below the cutoff, which is where the effective field theory actually works, and one region above the cutoff, which is instead where I don't know what goes on. It's the UV theory, and we don't have access to it, okay? Now, consider this integral at very large S, at infinity. It turns out that this vanishes because of the Froissart bound, which holds for basically S. If I divide by at least 2 powers of S, this contour vanishes here. Because of analyticity, we can deform this into a contour that actually interpolates between the UV, the blue, and the effective field theory. So it's a mixed contour. And the beautiful thing now is that because of unitarity that implied positivity across the real axis, we know that the integral on this part is positive. This is all more or less well known. And in summary, basically, it's telling us that the integral on this arc with radius any energy within the effective field theory, keep this in mind, is equal to the integral in the UV from that energy to infinity. So I defined this object, the arc, curly A n, which is thus the integral along this, and it's given by this expression within the effective field theory. But because of the arguments I just mentioned to you, these dispersion relations, this is equal to a UV integral. And moreover, because of unitarity, this thing, the imaginary part, is positive. This means that all arcs are positive. And now, the interesting part of this is that the arc in the infrared is calculable within the effective field theory. And in order for you to understand better what I'm talking about, arcs at tree level are nothing but the Wilson coefficient that I mentioned before, the coefficient of the energy expansion in the amplitude, okay? So they're really calculable, you see what they are, you can measure them experimentally. Now, the UV condition, because of this equality, can be imported into the infrared and becomes a consistency condition for the effective field theory. The fact that arcs are positive, or whatever other object you wanted to define in the infrared, was already pointed out in this beautiful paper some 15 years ago. Now, it turns out that there are more bounds than just this positivity. And it's easy to see this, because if you change the variables from this to some x, which is proportional to 1 over s, this object is equivalent to an integral between 0 and 1 of a positive measure mu of x to the n. And this object is called a moment. We're all familiar with moments, right? Moments, electric dipole moments, moments of inertia, etc. And in fact, it's very intuitive to see what this object actually do. If you think of a simple example, like a planet, whatever, a neutron star, a stone, an asteroid, whatever object, and we consider mu to be the mass distribution. This is a positive distribution, right? Because it's just the mass distribution. Then let's see what these moments are. The 0 moment, so integral over x to the n, x being really the space coordinate. The 0 moment is the total mass and sets just the units of my problem. The first moment is the center of mass, integral over the measure over x, so center of mass. And this can be at most r times m, if you think that all the mass distribution is localized at the very edge of the distribution. Instead, the second moment is of order x squared. This is actually the moment of inertia and is maximized when all the mass is distributed in a ring at the maximum radius. So you see from this intuitive example that the first three moments are actually bounded because we have three quantities, but their extreme are determined by two quantities, m and r. So this opens the door to ask ourselves, what bounds do moments satisfy in general? So we've seen that bounds on effective field theory arcs, which, as I anticipated to do at tree level, is like Wilson coefficients. So bounds on arcs are like bounds on moments, and the relation is given just by this change of variables. It turns out that bounds on moments are in one-to-one correspondence with positive polynomials between 0 and 1. And this is very easy to see. So take a polynomial positive between 0 and 1, which is just alpha some coefficients times x to the power of I, okay? And this is just, I take it to be positive between 0 and 1. We can shovel this into the integral with the positive measure that I mentioned to you before, and this has to be positive, just positive measure, positive polynomial, okay? Now, using the equivalence between arcs and these moments, we obtain a relation between arcs. So the sum of arc I times the original coefficient of the polynomial, alpha I, must be positive. It's a condition on arcs. You see now that by finding all positive polynomials, we will find all positivity conditions that relate arcs. So let me illustrate this for the case of the first three arcs. I put them on this just this plane in which we divide by the zero arc, and we have basically A1, A2 in units of 0, and S squared, which is the energy at which these arcs are defined, which basically is in one-to-one correspondent with the fact that here there is an integral between 0 and 1. So from an effective theory point of view, basically any value will be okay in this plane, even these little squares that I didn't manage to make gray in the presentation. So let's see some polynomials. Okay, polynomial 1, I put it in here, blah, 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 gives me the alpha, the 0 arc is bigger than 0. Polynomial x, a1, a2, and this is just the positivity of all arcs that I mentioned before, and basically cuts already the plane in here. There are other polynomials which are positive between 0 and 1, for instance, 1 minus x, x times 1 minus x, and this gives me two more relations. It tells me that the 0 arc is bigger than the first arc in units of energy, and basically they are all monotonically decreasing, and this carves out this smaller region. We can design another polynomial by taking x cubed plus this piece in which the x cube cancels out, and this excludes also this little triangle, and so on. And in fact, all polynomials of this type are captured by this formula. These are called Bernstein polynomials, just powers of x times powers of 1 minus x. This is the most general polynomial positive between 0 and 1. And when I include all of them, infinitely many of them, we find basically this curve. So the allowed region is basically in here. Now, typically when we deal with effective field theories, we are interested in a finite number of Wilson coefficient, in a finite number of powers of the energy. This is because effective field theories are intrinsically thought to be truncated at some order just for phenomenological application. So it's a bit inconvenient to have bounds which typically involve infinitely many arcs, that we need infinitely many bounds in order to say something about a finite number of arcs. It would be better to have a finite number of constraints for a finite number of arcs, of Wilson coefficients. And I'm sure many of you have guessed what the answer is. These are finding all positive polynomials between 0 and 1 with a given order, so of order at most x to the n, with n smaller than some n max. The most general such polynomial will give me optimal bounds which involve only a finite number of arcs. It turns out the most general polynomial of this kind can be written in this beautiful form. These are Q1, Q2, Q3, and Q4 are generic polynomials, but I take the square of it. So the square of one polynomial plus x times the square of another polynomial plus 1 minus x. This is the most general polynomial of order, of fixed order, where Q1, Q2, Q3, and Q4 have some fixed order themselves. I will mention this later. You can find it in the paper. Anyway, let me see what happens now. So Q1 square, okay, we put it into our measured distribution. Q1 square, Q1 is a generic polynomial, which we can write like this, but not necessarily positive. And it gives me a condition that on the arcs, that the sum of alpha I, arc I plus j times alpha j must be bigger than 0. For alpha I and alpha j, completely arbitrary now, not like before that they were not arbitrary. So it turns out this condition is exactly equivalent to requiring that this matrix of arcs I plus j must be positive definite. So for instance, for 4 arcs, we obtain this matrix, and this must be positive definite. This is known as a name, and it's a Hankel matrix, which might resonate with some of you in the audience. So all optimal conditions involving at most n arcs can be written in terms of these Hankel matrices and these 4 conditions. These 4 conditions come from the fact that we had 4 types of polynomials in the previous slide. The first one we have already seen, H1n is basically the same one which starts with arc 1. And then there are these ones which I will perhaps refer to as inhomogeneous because they actually involve this energy. And I remind you that this is any energy within the effective field theory. So for 3 arcs, we now get a finite number of conditions, which is the what I wished for before. And this reproduce this figure that I already mentioned. For 3 up to 4 arcs, instead, we can plot this in this 3-dimensional picture, and we get this beautiful banana. I will refer sometimes to this as banana just to evoke the shape of it. And you can go on and add arcs, always a finite number of them, and you always get a compact figure in the n-dimensional space of n arcs. So this is all beautiful. It carves out the space of tiers, but let me actually try to trigger a bit more your attention with some applications for this at starting at 3 level. We only mentioned the forward limit so far. At 3 level, the amplitude is just a polynomial in S squared, where the coefficients are just the C that I defined already in the introduction. And the question is what I already brought to you before, whether the scattering amplitude can grow fast with energy in some regime, at least. This is this idea of supersoftness. Particularly reminded that the amplitude as a function of energy can be flat, for instance, for Higgs scattering, can decrease for Baba scattering, can increase linearly with S, as in Fermi theory. And the question is whether some more exotic behavior is possible. I remind you that this is natural and infrared consistent. So in the 3-level approximation, arcs are actually very easily computable. You just put these ansatz in here, and this turns out to just be the derivative with respect to S. And so arcs are in one-to-one correspondence with Wilson coefficients. I apologize that in a previous slide I used a slightly different notation, but this is, I hope you're not confused by it. Okay, so this means that we can basically plot this, this banana, changing the labels of the axis directly with the Wilson coefficients. And in particular, notice that the bounds start with C2, the coefficient of S squared. This is related with this idea that the Froissart bound determines what contour vanish at infinity and determines from what Wilson coefficient we can start saying something. The fact that this plot terminates here implies that C2 is always bigger than C4 in its contribution to the amplitude. And in turn, this line here implies that C4 is always bigger than C6 in its contribution to the amplitude, and so on. So basically, this picture that I was looking for, which is the supersoftness, in fact, is not compatible with my bounds, because these equations are telling me that the C2S squared piece must always be bigger than the super soft ones. So we can interpret this basically as information about the cutoff. The cutoff of the theory must appear before these terms start dominate. So these optimal bounds involving S, actually, they carry information on the cutoff of the theory. And for super soft theories, they are telling us that super soft theories have a very low cutoff, so low that super softness is actually unobservable. You will never see, if you do an experiment, you plot the amplitude, you will never see that it grows like CNSN, because it's always dominated by the S square piece. And when the other one would like to dominate, bam, these constraints that actually tell you that you're hitting the cutoff. So just to illustrate within this little table that I mentioned before, the forward bounds, so from looking at forward amplitude, basically they bound all the coefficients in this vertical column, and they bound them to be within a banana. And it's interesting that any two coefficients, just two, are related by these linear constraints, while the other curved constraints, they involve at least three coefficients. But it's important that you have already constraints involving any two of them. There's another application which I found actually very interesting and has to do with massive higher spin. So massive higher spin resonances, they exist in QCD, in nuclei atoms, in strings, etc. And there is one feature that is common to all these cases, these real cases that I mentioned, which is the fact that the mass of higher spin resonances happens always to be heavier than the inverse size of these resonances. This is an example taken from some lattice QCD simulation. Lambda QCD is actually the inverse size of QCD resonances. And you see that all the resonances with high spin, like spin 3, spin 4, and so on, they're always above the cutoff. This is perhaps so familiar to you that, in fact, you considered it a fact. And the question that I would like to ask is whether, in principle, there could be higher spin resonances below the cutoff, for which we could write an effective field theory. Now, interactions between particles of higher spin, they actually grow with energy, up to an energy which is given by their inverse size, because this is how much you can localize the particles to scatter them, at most their inverse size, okay? When you compute the amplitude for the scattering of higher spin particles, it turns out, in particular the longitudinal part, so in that sense we are really scattering scalars, as I advertised before, but it turns out that the amplitude is given by this beautiful expression, powers of energy over the mass of the higher spin. And in particular, the maximum power of this is controlled by the spin of the particle. So this is, in terms of the language I used before, this is C2, and this is C2J, where J is the spin of the higher spin resonance. And when now we look at these bounds involving the scale S, you see that this contribution must always be smaller than this one at any energy S within the effective field theory. So if I plug in the biggest possible energy that I can think of, their inverse size, I find a beautiful bound, which is just mass of the higher spin bigger than 1 over the inverse size. Higher spin particles are always heavier than their inverse size. So this is a prediction of quantum field theory, not just an accident of the many situations that we've been looking at so far. So the The story that I've been presenting to you so far in the forward limit can be extended also beyond the forward limit. In particular, at 3 level now, the amplitude becomes a polynomial in S and T. And one piece of this, which is particularly interesting, is the Galilean term, so the coefficient of S squared times T in this amplitude. At 3 level, these coefficients can be mapped with derivative of some arc defined at finite t. The definition is very similar to what I've been mentioning before, just done finite t and exploiting the fact that the amplitude for very small t is analytic in S. So we have an expression of this type with now derivatives of t. And when we take t derivatives, these act on the imaginary part of the amplitude, and t derivatives of the imaginary part of the amplitudes are known to be positive since a long time. And this basically implies that we have another positive measure also in this case. And this implies other bounds like the banana ones that I've been mentioning before, one for each derivative of t. In fact, things are a bit more complicated because the t derivative doesn't just act here, but it also acts at denominator, where there is a t that comes from the existence of the U channel in that I mentioned before. And this can give some negative contributions, but it turns out that the negative contributions are always limited by the other moments. So you can still find a shape of your bounds. And now it's not just vertical, it's not just involving coefficients with the same power of t, but it involves a bit everything. It's a bit shady. That's why I colored here with these nuisances. And in particular, the optimal bounds that involve just a single t derivatives and up to coefficients of order s to the 4 are shown in this plot here. And you see that basically bounds involving t derivatives, this comma 1 is the t derivative, are mixed, appear together with things that have no t derivatives, C4 and C2. So this is the optimal bounds for these things. In particular, you see that this Galilean coefficient can now be a bit negative. It's not bound to be positive as if you didn't have this denominator, but it can be, it's bound, its negativity is bound, basically. It has to be bigger than a certain product of coefficients. There's another relation a little bit weaker that appeared already in this article. Now, in fact, as was pointed out in the recent work by Nima, Huang and Huang, we know also much more about this amplitude. In fact, it's not just positive, but the derivative with respect to t of the amplitude in the forward limit is given by a known function, because when you expand it in Legendre polynomials, you know the shape of the Legendre polynomials. They appear at all orders in their derivatives are related, and therefore you find more relations that roughly basically they connect coefficients in this direction. In fact, this can be also seen from the point of view of moments that I try to motivate so far, because basically this sum over L, you can think of it as an integral in the continuum limit of a positive measure, positive because the partial waves are positive. And this thing just gives you some powers of L. So you recognize this as the same shape as the moments that I introduced before, with the only difference that the upper bound is infinity. The implication of this is that the bounds don't have this upper straight line, but they are unbounded from above. But only the bound involving at least 3 guys survives in here, okay? In fact, at 3 level, crossing symmetry implies that the amplitude is a very well-defined structure, and in particular, it predicts that some of these coefficients that I've been putting in this table are actually related. So this one is in fact related to C4 because the amplitude only comes with powers of S squared plus T squared plus U squared. So we know that C4 is smaller than C2. Now we relate C4 to C2, 2, and this is telling us something about C2, 1, the Galilean coefficient. And it basically leads us to a two-sided bound on this Galilean coefficient, as was recently pointed out in these articles that appeared in November. So it appears that now, in addition to what I've been saying before about all the other coefficients, also the Galilean coefficient is tightly bounded from below and above. I will have some comments on this about loop effects later, keep it in mind. Okay, so the picture that emerges from this is that at tree level, when you also look beyond the forward limit, you have an expansion in coefficients. There are infinitely many of them, but only 3 can lead the amplitude, because the first one, the one that doesn't multiply any powers of s or any power of t, is arbitrary. We don't know anything about it. C2 is positive, as was known for a long time. C2, 1, as I just showed you, is sandwiched between 2 values, and all the other ones appear to be smaller. They are always subdominant in their contribution to the amplitude. Okay, so in the last part of the talk, I would like to discuss how this picture that basically is was motivated by, at least in their applications, by a tree-level ansatz of the amplitude, how this is modified when we actually think beyond tree level. And for simplicity, in what follows, I will actually think of the theory of a Goldstone boson, so where basically my amplitude starts at order s squared. Now, bounds are modified, and the reason is that infrared loop effects, they change the relation between the Wilson coefficients and these arcs. And I remind you that the bounds are on the arcs, they're not directly on the Wilson coefficients. So if this relation is changed, the bounds will also change. In particular, there are 2 effects that enter in this change. The first one is due to running. Running, for instance, a loop of this type in the amplitude gives a contribution which goes like s to the 4 log s times a loop factor. But there is another class of divergences, collinear divergences, diagram of this type, the same one but in the t-channel, gives a contribution which, instead of going like log s, goes like log s over t, okay? Times s squared, t squared. So the first type of effects modify the arcs by because arcs, I remind you, they are a bit like derivatives of s of the amplitude. Now, if we have a log, these derivatives will fish the existence of the log, and in particular, for sufficiently high arcs, so for n big enough, they will induce a 1 over s behavior in the arc. And basically, you see that when s is sufficiently small, so when the energy that we're looking at is sufficiently small, the bounds are completely dominated by this more relevant term. And this basically implies that these loop effects affect all bounds for arcs, for Wilson coefficients bigger than C6. This is due to the fact that there is this power. These ones are left alone, and here you will start having very relevant effects that modify the bounds. Collinear divergences, instead, they modify the t derivative of arcs, so the bounds at finite t, because they always come with these powers of t. And in particular, when you have at least 2 derivatives, k minus 2, you will get a contribution which goes like log s over m squared, okay? This is because we're expanding around very small t, and so the t-channel contribution is basically dominated by the infrared cutoff of the theory, which is the mass. This log s over m can be bigger when the scale separation in the theory is large, and basically these bounds alter any bound, sorry, this contribution to the arcs will alter any bound that involves the coefficient on this side, so with at least 2 derivatives. Let me just be a bit more specific And basically, running effects, they can be written in this form by computing explicitly. These are really running effects within the effective field theory. And you can compute them. Beta 4 is just given by C2 square divided by 16 pi square with some number, right? You can compute the others. I didn't write them, but they're easily computable. This is the two-loop piece, etc. But basically, you can cast them into running Wilson coefficients. So basically, the coefficient that multiplies s to the 4 and s to the 6. And the question that we would like to understand is whether the bounds that I showed to you so far, they actually apply to the running coefficients, to this Cn of s, okay? This would be fantastic, because it means that everything that I said so far also holds at loop level. In order to understand better what I will be talking about, it's useful to make a slight change of coordinates in the plots. Nothing fundamental, just a different way of representing them. So the x-axis remains the same, is still the coefficient C4 divided by the C2, but now depends on S, okay? But the y-axis, instead of this that gives the banana, now has this different dimensionless combination that basically produces this form. This extends all the way up to infinity. It's just a deformation of this banana. And this area is the bound that we expect at 3 level. Now, arcs are actually the suitable object to look to access the running coefficients. Because in fact, when the energy at which the arc is measured, is calculated, changes, you're basically accessing your amplitude at different values of the S. So you're really accessing the running coefficients directly. And in fact, you find that the zeroed arc is equal to C2. This is exactly like a 3 level, because C2 doesn't run. We are assuming a Goldstone boson, and the first coefficient cannot run by dimensional analysis. There are some corrections here that I don't write because they are small in perturbative theories. So there is no way, I mean, when these corrections are sizable, typically you're out of the validity of your perturbation theory. Not always true, but it's a bit, okay, anyway. I ignore this for the moment, it's okay. The first arc, instead, indeed captures the running coefficient. This, if you want, illustrate what I was showing here. And this is beautiful. It means that all the relation that involved the first 2 coefficients or the first 2 arcs will actually remain the same, but now with the running coefficient. The second arc, instead, receives a contribution, as I mentioned briefly before, which is inversely proportional to S. So this thing is very relevant in the infrared and will dominate my the bounds. Indeed, the real bounds, including loop effects, are illustrated by these color plots. The dashed lines, they report the 3-level naive bounds that we had before. So why different colors? Well, different colors basically capture here how far away you can be from the cutoff of the theory. Points which are blue, in fact, are very close to the cutoff. Points instead which are red are theories which can have a very large separation of scales. Particularly, let's look at this plot here. The feature that is new is that now there is an allowed region also below this area. This quantity equal to 1 is equivalent to the belly of this figure. And in particular, in our table of coefficients, where now I promoted all the coefficients to functions of S because there are running coefficients, the relation between C2 and C4 remains very similar because these arcs are not modified. But indeed, anything that involves C6 will be plagued by this contribution. Now, the bounds up here, in fact, they become a little bit stronger, but not very much, because here you're very close to the cutoff already, so this is not really an effect worth discussing. But an important implication is that this idea that supersoftness cannot exist is still there, just because the real bound with loop effects is stronger than the other one. Okay, so the supersoftness is still dead, even when we include loop effects. On the other hand, down here we have a region that now is allowed, and in fact in this region the bounds are much weaker. For instance, this coefficient C6 can now be smaller than 0. And in theories which have a very large separation of scale in which they are valid. In fact, look at the running, how it takes place. When you run towards the infrared, it turns out that all the theories, they actually converge down here. So it's good that the arcs allowed this area to be true, otherwise they would have been excluded at tree level. On the other hand, when we run up, a theory can either enter into the tree-level allowed region, or it can just hit the boundary down here and exit before ever looking like a tree-level theories. So in fact, there are this analysis shows that there are some theories that never actually fulfill the tree-level bounds. They are genuinely different. I don't know what they look like, but it might be interesting to think some more about this, because these evade the bounds, part of the bounds that I discussed so far. So the other type of infrared effects has to do with these collinear divergences. And in particular, they are due to the fact that my setup, the problem how it has been phrased, it's fundamentally a two-scale problem, in the sense that because of the requirement that the amplitude be analytic, we want t being smaller than the mass, so very small t. On the other hand, because we are interested in theory with a relatively wide range of validity, we want large s, much bigger than the mass. So we have a two-scale problem that eventually has some effect. Indeed, when you look at the amplitude, the loop effects that I mentioned before, the one in the T channel, gives a contribution of this sort. This is of the same, so it contributes to the S squared T squared coefficient, so the C2,2, but it's not of the running form. This is really related to an infrared singularity. And in particular, it will effect of this type to some power will also enter in all other coefficients with more and more powers of t. So all the bounds that lie on the right-hand side of this line, they will be affected by these log s over m square terms. And in particular, remember that the bounds that go in this direction that were pioneered by Nima, Huang, and Huang, in fact, they require at least, they involve at least 3 of these coefficients. And I remind you that these were exploited in these 2 articles, 2020, not 29, to put a bound on these Galilean coefficients. And now we can basically see how these bounds are altered. And what you see that indeed for energies which are not so separated from the mass, the tree-level naive bounds actually hold very well. But on the other hand, these effects are always there. All the bounds in T, so these horizontal bounds, will be affected. And in fact, the bounds will not be there when we take the limit m going to 0. Unfortunately, these effects are small for finite mass, just because we have a log, a loop factor, etc. But for vanishingly small mass, the bounds are no longer there. These are the real curves. So instead of having this is the tree-level relation, the dashed line reported in these papers. And in fact, as the mass goes to 0 with respect to S, we diverge from the bound. So the upper bound is no longer there. Okay, I think that's enough, 50 minutes. So in this seminar series, we divide the world in 2, where we have an effective field theory, where we have a UV theory. And in this talk, I basically have imported the most basic assumption about the UV causality, unitarity, Lorentz invariance, and locality. And I've presented them in terms of moments to put some constraints on effective field theories. First of all, I showed you that of all the possible coefficients, there are only 3 or 2 that can dominate. I showed you that this idea of supersoftness is actually never realized in practice, although consistent from an infrared point of view. And finally, I show you this nice application to the fact that higher spin particles are always heavier than the cutoff. In the last part of the talk, I also discussed running effects calculable running effects within the effective field theory, and in particular the fact that they affect all bounds with coefficients which are have sufficiently many powers of energies, or coefficients that have sufficiently many powers of t. Thank you very much for the attention, and yeah, that's it.